First step is always trying to see if everyone is hearing correctly. So if you cannot hear, yes, if you cannot hear, you can read the chat. And so today I will present to you, I will do a very quick overview over the semantic technologies. And we are here at Cognitum working a lot with semantic technologies and all the stack around semantic technologies. So in the first part, I will introduce you to the standards and the technology that are used inside the semantic web and all semantic technologies. And then in a second part, I will do hands-on practical examples of how to actually create or modify things, knowledge base ontologies using our software stack here that we develop at Cognitum, and especially I will show you Fluent Editor, and we will see how to modify and create ontologies using Fluent Editor. So let's start by the beginning. The beginning is description logic, and this is because description logic is underneath all semantic technologies, and is one of the let's say the main logic that is used in OWL. But we will see there are other subset of this logic that are used. And so this is just a quick introduction to let you understand what are the ideas behind description logic. So it is used a lot in semantic web, and in this logic there is no unique name assumption. So you can name things differently, and they will not always be the same if you don't specify this. Then there is this open word assumption. So open word assumption is the main assumption made by the reasoner in description logic, and it states that if something is not stated, then it is unknown. So this is very important because it's not very intuitive for us to understand this. So it generally causes some problem of understanding why the reasoner is not retrieving all results that you were expecting. But on the other hand, this is useful for the reasoner and in general for the semantic web, because if you have this assumption, so that if something is not stated, it is unknown, then you also can extend the things that you are saying, because you have not taken assumptions about the things that you didn't know. And so you can always extend the knowledge, and you will always be sure that everything is reasoned. And so this, in reality, gives a possibility to extend the knowledge without problems in reasoning. Okay, then after I will go a bit in detail of the possible restrictions that you have on this logic in order to make reasoning more fast and things like this. But right now, I wanted just to give you an idea of what is underneath the technology that I am showing you today. What is the semantic web? So the semantic web and semantic technologies in general, the semantic technology has been developed with in mind the semantic web. And so they start like this: that you have two main types of files. Then the syntax can be different, but two main types. And you have OWL and RDF. And these OWL and RDF are generally expressed in XML, but there are other syntaxes for them. And so these two are the main languages. There are others that are used directly inside web pages of XLs, but these are the main languages that you use to develop ontologies. And as you see, the files, they can be wherever you want. So you can have files in the web, or you can have files inside a database, for example, or for example locally. And the whole point of the ontologies is the fact that they can reference between themselves. So in general, a local file can reference to a file in the internet, and or the file in the database can refer to a file in locally and things like this. So, and this is the main idea behind semantic web: give a way to describe knowledge, at the same time make it possible to extend this knowledge simply. And then on top of this stack, you have SPARQL. That is another standard. All of these that you see in this page are standard W3C standards. And SPARQL is a query language using which you can query the content of your knowledge base or the things that you have in your you have modeled. So in general, SPARQL is quite expressive. You can express quite a lot of things using SPARQL, and it's a very nice language because you can do federated queries. So you can do quite complex query using SPARQL, and in SPARQL the idea is the same that it is for the whole semantic web. So it's extensible. So you can take an ontology from one source and then, or take from more than one source all at the same time, and things like this. Okay, so this is the general architecture. Then let's dig directly into OWL. So maybe I should start by OWL and RDF. There are languages to describe knowledge. So there are languages in which you can describe, you can model the things that you are, for example, that you want to model. That can be the reality or your particular system, and you can express relationship between them. And then, as all of this is a standard, on top of these technologies, you have the reasoner, and you can also reason over the things that you have written, so that in general, after modeling the system, you will have something that is more than what you have written, because there is also reasoning on top. So in the OWL standard, there is a definition of different reasoning profiles. So in this case, you see I listed the ones that are defined in the standard. So you have OWL full, that is the profile in which there is a more complete profile, but to our knowledge, at the moment there is no reasoner for it. Then you have OWL DL, EL, QL, and RL. So going from the top to the bottom of this list, you are going from the more efficient reasoning, the less efficient reasoning, to the more efficient. So you need to take into account this while creating an ontology. And on the other hand, going from the top to the bottom, you go from the most expressive to the less expressive, let's say, more or less. In reality, the first two are the most expressive, and the last three are more or less the same. They have the same expressivity within them. So DL is description logic, so it's the one I was speaking about at the beginning. And description logic has benefits from many years of research. So there is a well-defined semantics. There is formal properties are well understood, and there are known reasoning algorithms. So DL can be quite efficient for particular reasoning, but in general DL is exponential. The time it takes to finish DL reasoning is exponential with the number of things you have. So it can grow very fast the time you wait for it. There is a theorem that says that everything can be, every conclusion can be reached using description logic, but you don't know how much time it takes. So in general, it can grow quite fast the time you need to wait for the reasoning to end, and this is why it's one of the less efficient. But on the other hand, it's the more expressive. The expressivity you have in DL is very high. Then you have the three others that are EL, QL, and RL. So EL is one subset of DL, so another logic that so in which facts can be reasoned in polynomial time, and RL also facts can be reasoned in polynomial time for most cases. The nice thing is then that RL is called RL because it's rule language. So using RL, you can generally express all the things that you can express in a rule language, and it can be implemented using rule engines. And then QL is another profile that is optimized for when you are interested in reasoning while querying. Then there is OWL-full, that is the one that has the more expressivity. And OWL-full is a way in which you can let's say define meta knowledge. So using OWL-full, you can, for example, you can describe knowledge about knowledge. So for example, you can say that you can define the relationships between two different ontologies. So to say that one ontology depends on another ontology, or that one ontology is incompatible with another. All these things can be reasoned and can be expressed using OWL-full, but to our knowledge there are no reasoner at the moment that use OWL-full. But I think this was added in the standard in order to think for the future. In fact, that the standard is some standard that needs to be the same for a long time, and so they are adding as much things as possible, so that in effect when a reasoner will be there, the standard will already exist. So let's dig a bit further, and if we go further, we can see here I took this image from the OWL definition, the standard. You can find this at the link you see down here. It's the link to the official W3C standard. And then when you see this graph, you will see what it means to create an ontology. So in this definition in the standard, in the OWL standard, there is a clear distinction between the ontologies and ontology documents. So the ontology, that is the one I am showing you in this graph. The ontology is the model, the abstract model that you want to write, while the ontology document is the actual document that the physical document that will represent this ontology. So, for example, an ontology document will be an XML file or a link, an XML file inside a link, or triple or things like this, while the ontology is the generic abstract idea of the ontology you are writing. And so the ontology structure looks like this: that you have the ontology is defined that it contains actions, and each time you see a star, this means that you can have more than one. So you can have how many actions you want. Each action can be annotated. The ontology also can be annotated, and in each annotation can be annotated also. And then you have this important distinction. So you have three different ways of importing things in an ontology. So you have, in general, you can, in reality, this is a bit abstract. So in reality, mainly you have two ways of importing an ontology in OWL. So one is doing an import of doing an import, and another is by referencing this ontology. So these are two distinct things, because when you reference, you are just referencing some IRI, and you are using this ontology that you are referencing because you need some concept or some entities that come from this ontology. While if you import an ontology, then in this case you want to import the whole content of the ontology. So if you import, you are somehow you need to think that you are adding to the statements you are making. You are adding all the statements that already exist in the other ontology. This is very important for the reasoner, because standard reasoner are using when you reference, they are not using the reference to reason, while when you are importing, they're actually using the imported ontology, for reasoning. So it's important to have clear this distinction because sometimes you can maybe import some ontologies, but you don't need to reason on them. So it's better to reference them. So it's important to have this idea, to understand what is this difference. Then in general, each ontology has an IRI and a version IRI, so it can have many versions. I don't know if you know, but IRI is you can think of this as URI, so as the links that you see in your browser. They are not exactly the same, so they are more than URI, but the idea is the same, let's say. And so IRI are generally used inside the semantic web and in the ontologies to describe things, to give a unique name to things. So generally the names of the things looks with a namespace that is an IRI plus the name. And generally the namespace is defined inside the ontology. So generally this is the ontology IRI. And when you import or reference other ontology, you are referencing or importing this through an IRI. Okay, so next. The annotation structure. So this is another very important part of the OWL tool. I just take a couple of them, so they are not very. I'm not showing you everything, just a couple of them, because I think these are the most interesting from the practical point of view when you are actually creating ontology. So annotations are quite widely used in the semantic web because they are a very simple and nice way to give, for example, human-readable labels to things that you define, or also it's a nice way to, and then a nice way, for example, to give translations to elements. So, for example, you can for the same entity, you can name it in different languages. And so this is why annotations are widely used. And the main ontology that defines a lot of relations and properties for annotation properties is SCOS. And you can use SCOS to extend your ontology. So the annotation structure looks like this. So you have the annotation that can have some value and property. And then the annotation can have annotations, how many you want. And the annotation value can be one of these. So what it means is that inside your ontology you can annotate everything. So an IRI, but also some literal or whatever you want. And you can use a property. So there are generally defined properties, and in here you can also define the relationship between properties, annotation properties, and things like this. But in general, the annotations are mostly used to define labels or to define other information that you cannot directly use inside the ontology. Taking to mind that mostly generally annotations in OWL are first-class citizens. So if you define a relationship between annotations or things like this, you will, in theory, the reasoner will also use this. So if you want the reasoner to be efficient, try not to create too many complex relations between annotations, because in general, probably you can do this in a simple way. So then, let's go to the next. So right now I introduced you very quickly to the abstract idea that is behind OWL and what is the definition of OWL and what are the main components of an OWL ontology. Now I would like to go on RDF. That is a subset of OWL. So all these technologies have been created one on top of the other. So you have RDF, and then on top of RDF, they have built OWL. And so RDF is a subset of OWL, Why? Because in RDF you can express much less things than in OWL, and also because RDF is a language that allows you to express things that can be represented on a graph. So to give you just a quick idea of what it means representing on a graph something, is this sentence. So you can say John gave Mary a book about frogs. So this is already a quite complex example because it's a sentence in which you have that you have an action that relates between them Mary and then book, and then book is about frogs. So it's in a graph in general you can express binary relations. So this is not obvious how you can represent something like this in a graph. And so on the right side, I am showing you the way in which you can do this. And this is the way in which, in general, this is done in a RDF graph. So you can express this in a way in which, okay, we added here some other things on top. So and this is because we have you can think that we have defined other sentences about this about John and Mary, for example. And so you can think of this like this, that you have John is a person and Mary is a person. And then you have this event that is some giving event, that is this gave. And then this event has an actor and a recipient. And the event has an object that is a book, and the topic is frog. So as you see here, everything is binary, but the concept, the thing we are expressing is not binary. So this is to give you an idea of how in general you can use a graph to express knowledge. And this is so in RDF you are sure that what you write in RDF in the last part, also if what you see in the last part is not RDF, is a natural language, but you can think that in the last part you have RDF sentences, let's say. It can be expressed in a graph, so you can go from the left to the right side and come back. So RDF has two parts. So you have RDF and RDFS. RDFS is RDF schema, and is a very simple. You have in there very simple relationships that can be used to create relationship between entities. So in general, RDFS can be used to create some simple taxonomy or things like this. So RDFS is very fast, and some graph databases implement RDFS, but you need to keep in mind that RDFS is not very expressive. So it's in the scale of the profile. This is not a profile, but in the scale of the profiles, this goes in the lower scale, so in the after RL. So it's not very expressive. But the fact that it's not very expressive also gives you the fact that everything that is expressed in RDF and RDFS can be expressed in a graph. While the contrary is not true. So it's sorry, not the contrary, but while it's not true that everything that you can express in OWL can be expressed in a graph. So there are some examples of this. For example, you cannot express on a graph, or maybe on a graph you can, but RDF graph, you cannot express things like some values from. So for example, say that the two, an instance and a concept are related between them. So for example, that every cat is John. You cannot express something like this because it's something that is like generic and it's difficult to represent on a graph. Or the cardinality relationships or generic property value restrictions. So these kind of things are very difficult to express. You cannot express them. So I think this is very important because it gives an idea of the fact that OWL is more than RDF, and using OWL you can express things that in RDF you cannot. As we were saying before, going up in expressivity, you lose efficiency. So it's also true that if you start to use the OWL, things can be slower than RDFS, but not always. For example, RL and EL have efficiency comparable to RDFS. Okay, so this for RDF, and so this is the generic idea of what RDF is, standard of RDF, and what you can do using RDF. As for the previous example, I will after go to some practical cases and try to show you how to deal with OWL and RDF in real cases. And now I would like to go to the next part. This is SWRL. So SWRL is another standard that can be used together with all these technologies, so together with OWL, RDF, and SPARQL and everything. And SWRL is a very nice language because it's a rule language using which you can define rules. And so if you take the expressivity, or let's say the things that you can say in OWL or in SWRL, you will get a graph, a graph like this. So you will get that things that can be expressed in OWL some of the things can also be expressed in SWRL, but they are not completely overlapping. So you have that some things that cannot be expressed in SWRL can be expressed in OWL, and the contrary is true. So this is why it has been added, because it's giving some additional extension to the possible things that you can say in OWL. The part of SWRL that is included in OWL is this one, and it's called the DL safe part. So it's called DL safe because it's a subset of SWRL in which there are some restrictions with respect to the full SWRL language, and the restrictions generally are that you cannot create new instances or new concepts using SWRL rules in DL safe. So this is some restriction, but this was added in the standard because it's very important for reasoning. In the sense that it's very important for reasoners. If you are outside DL and SWRL, the full SWRL is outside DL, then you are not sure that everything will be reasoned. That everything can be reasoned, that you do not have this certainty, and this is why only the DL safe part has been added, because OWL plus the DL safe part of the SWRL still can be reasoned, while if you were taking the whole SWRL, you could not. So this is SWRL. The very nice feature you have in SWRL are built-ins. So built-ins are this part of SWRL, so this extension of SWRL that allows you to use some function or define functions to extend the functionality of SWRL. These functions, in theory, you can define whatever function you like. There are still some categories of functions that have been defined in the standard, and generally these are the ones that are used. So these are the categories. So you have built-ins for comparison, math for Boolean, string, date, time, and duration, URIs, and lists. So in general, the most used are for comparison. This is, for example, that you can express in SWRL rule, you can compare values. So say that express a rule in which you are searching if a value is greater than another, or things like this. Then you have the math category, in which you have all functions that deal with mathematics. So, for example, the square root, or for example, the multiplications, or things like this. Another very interesting one is date, time, and duration. This is a category in which you have all functions to compare date time. So, for example, that to see if a date is greater than another, or to see if the date is less than the last month, or things like this. And then the other are other extensions, but I think these ones are the most used. The only problem you have with built-ins is that some listeners do not support it. So, for example, Hermit is not supporting built-ins because there is no theoretical assurance that of completeness. So when using built-ins, you're not 100% sure that everything will finish. So it's related to what I was telling you before of the else-safe. So it's not 100% sure that everything can be written when you are using built-ins, but still they are so useful that in reality a lot of people are using them, and it doesn't seem to, in practice, it doesn't seem to have a big problem for reasoning. Also because in general rules can be treated quite efficiently. Yes, and there are other reasoners that support built-ins. So, for example, Palette is supporting them, but not all of them. And for example, in Fluent Editor, we have implemented a rule engine that is is actually reasoning using built-ins. And in the current version of Fluent Editor, you will find the comparison built-ins. While in the next release, we have implemented many other built-ins, mostly the one in the datetime and duration categories and in math. And okay, so this is for the built-ins, and yes, I think for the built-ins that's all. And so this was the SWRL part. And so this was the last piece of the things that are generally used inside while modeling knowledge using semantic technology. And generally you will find these three pieces together in an ontology. So this will be an XML file or some other format. And generally you will find inside a combination between SWRL, RDF, and OWL. So in general, an ontology is an ontology is composed of more than one of these elements. So to go on, now that we have seen what are the pieces that compose an ontology, we go to what is SPARQL. That is the language to query actually these ontologies. So SPARQL is working on graphs. So when you are using SPARQL, you are actually querying graph databases or RDS databases. But SPARQL is a very expressive language. You can express a lot of things in SPARQL, and queries can become very quickly very complex. And in general, what you do in SPARQL is that you express graph transformation or graph patterns. So in general, you can express things like that you want this node to be connected to another node or things like this, or graph transformations. Then in SPARQL you have mainly three sections. So you have a first part that is the prefix. So in prefix part, you can define the relationship between prefix and namespace. And this relationship will be used locally in the query to find the elements you're using. I will show you an example after. The other thing that you have is select. So, for example, select is I think what you can think of in SQL. So select is selecting the things that you have inside that you have asked in the query, and you can use aliases, so you can change the name of the variables you are asking for. You can ask for everything, for things like this. Then we have construct. And construct is a way in which you can do this. You can do a query, and the construct clause will create new triples from the results that you get. So this is very useful when you want to, for example, change something inside your database. So you can create these new triples and then put them back inside the database. Or, for example, construct is used, for example, there is some implementation of RDFS reasoning using SPARQL, and in this case construct is used to create the new reason triples or things like this. Another thing you can do is ask. So ask is a way in which you will tell the SPARQL processor to return a Boolean result, and this Boolean result will be true if the things that you have asked, the things that you were searching for, so the graph pattern exists, and it will be false if if this graph pattern do not exist. Then after this, this is in order. So in general, you need prefix, then select, then the content of the query in which you ask where, and you give the graph pattern you are searching for. And then after, you can give filter, limit. So filter and limit, there are that you can filter. There are quite extensive functions that you can use. There is a regex and things like this. And then you have limit, offset, and all these kind of things. It's interesting to know that in SPARQL queries, the graph patterns can be nested. So you can have a graph pattern that then you have another graph pattern, and the two graph patterns are merged together, or you do the minus between two graph patterns or things like this. But in general, I think what is important to remember is that SPARQL is not looks very similar to SQL, the syntax, let's say. Also, it's not exactly, but it looks similar. But underneath, the SPARQL is very, very different, because when you do some queries, you are always searching inside a graph. So this is very important, because it's very important to remember for efficiency. Because if you remember about this, then you will know that some queries, it's not a good idea to make some queries or some other, because some of them will not be efficient in a graph. So this, I think, is important to remember. Then, so I want now just to give you a quick example of what it means to do a SPARQL query, and this is that, for example. Let's start by taking the fact that we want to make a query that is in which you have we define the prefixes. So this is the actual SPARQL query. So you define the prefixes, and we define two prefixes. So RDF and NS, that is my namespace. And I tell the SPARQL engine, I tell him what is the namespace corresponding to these two prefixes. And this is used only locally inside this query. You will not use it for when returning, for example. And so it's just used by the preprocessor in order to know that this one should be changed to the full namespace /John. Okay, and then you ask a query, and you said select. Here, this is the way in which you define variables in SPARQL. So it's question mark X, question mark Y, and then you say where, and then you say this is the graph pattern that you want to search for. So you want to search for a node that is called my namespace /John, and then you are searching for relationships, links from John, a link that is called question mark X to some value or some instance question mark Y. So if a graph database is well implemented, so it will very quickly find this node, because it will have somewhere some index that tells him where this node is, and then it will start from this node, because you tell him that this is the place where to start, and it will go it will follow the links. So these are the question mark X links. And then it will find out that there are two nodes, so this will be the question mark Y, and it will retrieve this table. So you will get back that X says is these two, and Y is these two. So this is just a really very simple example, just to show you what it means doing a SPARQL query. And I think this is very important to keep in mind while working with these technologies. Because you need to remember that the things that these technologies are doing are quite different from the one that the standard, let's say, SQL databases or things like this. This is important also to keep in mind, because you can do a lot of things that you cannot with SQL, and some of the things that you can do in SQL you cannot do with this kind of graph. Or maybe you can, but it's not a good idea. So it's important to keep in mind this distinction. So this was all for the introduction. So this was the introduction about semantic technologies and what you can do with this, and what are the pieces that you get while working with semantic technologies. So now we will go to practical examples. The practical examples I have prepared are quite simple, I hope, and in all of them I will use Fluent Editor. So Fluent Editor is a tool that we have developed at Cognitum, and it's part of our the whole ecosystem called Ontology, in which we are building various tools using semantic technology. So Fluent Editor is an editor for ontologies, and in Fluent Editor everything is compatible with OWL, so you can import ontologies and export ontologies to OWL or to RDF, for example. You have full compatibility with Protege. You can export and import from Protege. But the difference is that inside Fluent Editor we are using a controlled natural language, and this controlled natural language is completely compatible with OWL. So if you see here, if you go in the XML preview that is down here, you can see that this sentence that is in CNL, so in Ontology controlled natural language, is like Sophie is a giraffe, and this translates to this sentence in OWL XML. So as you see, we are distinguishing in CNL, we are distinguishing instances, so named individuals, from concepts, so classes. And so in this case you have that in CNL, all things that are uppercase are instances, and all things that start with lowercase are concepts. And then here you see that in OWL this is not important, because in OWL there is not this distinction. But in our CNL this is like this. But this doesn't mean that you still can define things as in OWL with the same name, and this is a property of OWL. So in OWL you have what is called panning, so you can define two or whatever number different things with the same name, and then the reasoner will automatically understand from the way in which you are using it. We automatically understand who is what. So in CNL you can also do this, but you will see the difference in CNL. But you see that in OWL they are translated in the same way, and this is one thing. So this is, for example, a way to define a class of searcher. Then you have a way, for example, to define subclasses of things like this. So in Fluent Editor you have this taxonomy tree here, in which we divide things by where they are. So for example, they can be a thing. So a thing is a concept or an instance, so a class or named individual. Then you have relations. So for example, you have eat, for example. So it's like this: every lion eats an impala. And so relations are relations between concepts or instances. And then you have attributes that are relations between some concept or some instance and a value. So in the taxonomy tree you can see all relationships that have been reasoned, that have been found inside the ontology, and this is your ontology. So inside here you have the whole ontology that you can add comments or things like this, and then you can export it to OWL or RDF. So another thing that you can do, for example, is ask queries. So as you see in blue, these are the keywords that we use in CNL. So everything that is in blue is a keyword. And so in this case, I asked, well, what is a thing? And I got back everything. So everything that is inside the ontology, and this is the answer to this question. But you can ask, for example, what is an animal that, for example, eats. And as you were seeing, we have autocomplete, so everything that you write inside Fluent Editor will be autocompleted with the possible things. So, for example, after every, you can have only concepts. So this is why here you have only the concepts that are defined inside the ontology. So things like this. So, for example, if you start with an uppercase and you write Sophie, then you will get auto-completed the properties or the relations or the attributes that can be associated with Sophie. And you can define whatever thing that you want. There is no restriction. You can add, for example, an attribute, and so this will be added in real time also to the taxonometry. So the queries that you can make here can become quite complex, and you can there is quite complex, quite extensive expressivity. So you can ask very complex query. Now I don't even know if there is things like this, but maybe there is. And when you get the answer, no, there is no one like this, so I will just ask for that it. And when you get the answer, you get here the instances that answer to your query. Here you get the concepts that answer your query, and here the super concepts. Okay, so this file, you can find it in File, New, and all the files I will show you come from this. These are templates that we are adding in Fluent Editor to give an introduction of how to use Fluent Editor and things like this, and they are highly commented, and you can look at them. So the other one I will show you now is the Italian dinner example, let me search for it. Yes, here. So this example is an example that shows you how you can use the full power of semantic technologies to inside Fluent Editor. So in this case, you can define a namespace of your ontology, and this namespace will be used for when exporting. So all the things that are like this will be exported using this namespace. Then you can import ontologies. So, for example, if you add this line that is called references to 2 points, you will find this in the autocomplete. So it's like this, references. When you do this, then the references will be imported, and this reference will be used to reason. And because in this case, in Fluent Editor, we have, I was telling you before, we have a distinction between the things that are actually imported and the things that are not imported. So if you define a reference, an IRI like this with parentheses, then it will be imported. Without parentheses, it will be just reference. So in this case, what is important is that when we import a reference, then we also autocomplete things from this reference. So you can see this here, that everything has been imported, and you can use them to define other things inside your ontology. And then you can, for example, ask queries also, like you were doing before, and you will get back the answer for the queries. And these queries will take into account everything that comes from the references because you are importing them. If you were not importing them, so let's make an example. Right now, I will remove the parentheses. So if I remove the parentheses, right now the things are not used. So you see, right now I have only things that come directly from the ontology, and if I will ask a query, I will get back only results that are defined directly inside the ontology. And this is the standard behavior, because right now, without the parentheses, we are not importing the things, and we are just referencing them. Another thing that can be interesting is that when you add a reference, here on the bottom part, we are automatically processing this reference and trying to download it. In this particular, when you have parentheses, in this particular case, you see there is a reference error. And this is because this URI doesn't exist. So we try to download this, but it doesn't exist. So you can then click here and, for example, browse and give a local copy of this, for example, or things like this. Okay, and another thing that maybe I forgot to tell you before is that down inside here we are always showing also the description logic equivalent of the sentence that you have your mouse on, so you have your cursor on. So in this case, you can see the description logic equivalent. I don't know if someone is interested in this. It depends if you know description logic or not, but we find when you know a bit description logic, sometimes it's very useful to disambiguate or things like this. And then, like I told you before, you have the XML preview in which you can see the sentences. You have two formats, RDF or all XML. Okay, and you see in RDF, just to again stress this, in RDF you have the namespace that you have defined here. So it's and every element have defined this namespace apart from the one that comes from the reference. So, and this is the way in which you use the prefixes. So in this case, you are saying that pizza comes from the pizza ontology, and the pizza ontology has this namespace. The namespace of the pizza ontology will be taken either from this, either from when you import from what is inside the ontology, what is defined inside the ontology. Okay, so this was the pizza example. And now I want to show you another example, that is this one. This one comes from, again here, the book reference. The one before was the Italian dinner. And so this example is in this example again, we are importing an ontology, beefsteak in this case. Just to show you that, for example, here we are importing this ontology, we are downloading this and then finding the namespace inside, and then when you get the RDF preview, you can see that we are actually using this the namespace inside to define the things. So for example here it's called, we are using this namespace to define has author. Another interesting thing is that you have annotations. So we are downloading from the reference. We are downloading the annotations associated to things that you have defined inside your ontology. And you can also everywhere in Fluent Editor add annotations, local annotations. And when you add annotations, this will stay inside your file and will be remembered. And it will be also exported to OWL and everything. And then, as always, you can use this window to reason over the ontology that you have. So yes, I think that's all for what I wanted to show you on this. So let's go to the next one. These are all very quick and simple examples just to show you what you can do with Fluent Editor. Then if you have any questions or if you have any doubt of how this is working, I can answer to them. So let's take this example. This is the server example, simple AT infrastructure. So this example is interesting because you have many things at once. So the first thing that we have here inside is SWRL rule. So let me find it. It's here. So just to show you how it looks. So you can write this in this way. So you say that if a server hosts an application, that the application runs on the server, and this is how the rule looks like in OWL. So this is, as you see, we were speaking about this before. It's DL safe rule because it's a DL safe subset of SWRL, and then you have the body, the class, and the head. Okay. Another thing we have added that you could be interested in is Sword debugger. You can find this in Tools, Run Debugger. And the swear debugger, this is a debugger that you can use to see how the reasoner is, I will come to this after, how the reasoner is actually using the swear rule that you have in your file to reason. So in this case, for example, here you can see that 3 times this rule was fired, and by opening this, you can see that this rule were fired because server to an application to fulfill the rule, and so you know that application 2 will run on the server. And this is, for example, the same is for server 1 and application 3, or for server 1 and application 1. So this is interesting to know what actually is happening behind the scene. And just to be clear is that what you can do is using this, you can, for example, ask about this. And as you see, this, when you ask runs on a server, you will get that these 3 applications that were the one that were fired by the swear debugger. But what is interesting is that, just to make this clear, is that the reason what it's doing is that you have your ontology, you define rules, you define relationship between things, and then when you ask the reasoner will reason everything. So it will also give you back the results that are not directly stated in your ontology. So for example, in the ontology, we stated that server 1 hosts application 1, but we haven't stated that application 1 runs on the server. But we got this answer because it has been reasoned using this rule. So another interesting part of another tool that I think can be useful is the materialized graph. So the reasoner that is here is using a standard reasoner, in this case Hermit, but it can be changed, and it's using full OWL DL reasoning. So you are using description logic to reason. So it can be slow sometimes. And so this is why we have also implemented the materialized graph. So materialized graph is a part in which instead of reasoning using all DL and using a standard reasoner, what we are doing here is that we are you can decide the profile that you will use to reason. So for example, here in this part, you can decide the profile. Right now we have implemented the RL profile and the DL profile. So these 2 profiles will affect, changing this profile will affect the materialized graph. And then when you have some sentences, for example, let's try, well, what is an application? You will see this kind of window if some sentences that are inside your file are outside RL. This can be a problem because if sentences are outside RL, it's possible that not everything that needs to be reasoned will be reasoned. In our case, we are using something that is a bit more than RL. So sometimes you will be able to reason also if not everything is in RL profile. But in general, if you want complete reasoning, you should be careful about what things are inside RL profile or not. So you can also say that you don't want to see this warning again, and in this case it will not be shown. But here, down here, you will see this icon that tells you that some sentences are outside RL profile. So if you want to know which sentences are actually outside RL profile, you can click on validate all to RL. And in this case, you see there is this sentence that is outside RL profile. And you can see here why. There is the description of why it's outside RL. So this is very useful when you want to build an ontology using RL profile and you don't know which sentences actually are not in RL profile. Okay, so then here, what I think is interesting is that here the query that is done, as I was saying, here we are using a different way of reasoning, and the query that is done here is done to actually a materialized graph, and this is why it's called materialized graph, because we are before reasoning over the ontology and materializing in a graph everything that is possible to be materialized, and then we are querying the graph using this query, and this query is translated to SPARQL. So, and here also you have quite a lot of expressivity, but underneath we are translating the query to SPARQL and retrieving the result from SPARQL. Furthermore, in this view we are showing much more information about instances. So we are showing instances and showing all properties, all attributes that relate this instance to other things in the ontology. The last part that I think can be interesting is this SPARQL tab. So here, and the SPARQL tab is querying the same graph that has been created in the materialized graph, but they're actually using SPARQL. So in this case, the only difference will be the querying type and the result type. So here you have the query, and here you have the result type. It's here. So this is the same that you see in the other, just that in this one you have the CNL query language and CNL result, while here you have SPARQL query language and SPARQL result. So now that I showed you, let's say, the way in which you can use Fluent Editor and how to access the elements of the ontology and things like this, I want to show you something that is some of the extensions that we made on the standard, because this is not fully standard, so it won't be exported to OWL, and it's more we are using mostly in our application to add functionalities to the things. So the thing that we have added on top is this that is called they are called model expression. And model expressions can be written in this way. So you can say that every customer must have priority a priority. So this is stating that you want that all instances of the customer will have priority a priority. So, and then you can ask the reasoner, and this is translated to standard reasoning, and we are using this to reason if things inside this ontology are fulfilling the modalities. And so when you click on this, you will see that elements in your ontology will change color. And depending if they fulfill the modality or not, they will have this color. And then if you click on one of them, you can see, for example, this is red, and it's red because every server must have status either operable or inoperable. So then if you change this, the status of this server, you will see that it will become green. So this is, I think we found this very useful, and we have used this quite a lot of time. And it's very interesting for making constraints on the actual things that you can or cannot state. Okay. And then just to go to the last example that I want to show you, and this is this one that is the last one, the simplicity with active rules. And in this case, the example is very similar to the one I was showing before. The additional thing that you have on top of this is that there is another extension that we made on the standard, and these are active rules. So active rules is a way in which you can write a rule. So if a server is connected by and then the difference is that when you define this rule, inside the rule you can execute some knowledge. Some code, in this case a C# code, and so then you can modify the knowledge. So, and this is just to show you another extension that you can use while using our CNL and Fluent Editor. So just to finish, if you want to see Fluent Editor help, you can just click on the help, and you will see the things that you can express in Semantic Web CNL standards, and that translates to Semantic Web and everything that you can do using Fluent Editor. In Fluent Editor, we have implemented everything that is in OWL, so you can express, for example, all kind of SWRL rule you can use built-ins. So, for example, here you will see, for example, this is a way in which you can express comparison built-in, use comparison built-in. So, for example, the value is greater or equal to 0. And right now we are implementing all other built-ins that are there. Using Fluent Editor, CNL, you can also define, for example, data type, and this is another very nice extension that there is in OWL2, so that you can define your own data type and use this data type to constrain, for example, the value of something. So, for example, this is the way in which you express this in CNL, and this is the way in which you express this in OWL. So it's a way in which you can say that some value is something that needs to be a combination of these. Then you can define, for example, this is another way in which you can define data types, for example. And then, for example, you have also the possibility of cardinality restrictions or things like this. And so you say that everyone at most has something. And another nice thing, for example, you have ASCII, for example, that is another OWL2 property, very nice, in which that is used generally to constrain instances and things in order to have to overcome the open word assumption, and this is very useful. Okay, so this is more or less all. If you are interested in Fluent Editor or other things that we are doing, you can contact us and we will be happy to help you. We are also developing server version of this of the whole stack, in which you can use semantic technology for very big ontologies, because you need to think that Fluent Editor is not written for very big ontologies, but in this case there is a server version, and also you can collaboratively edit ontologies using Fluent Editor and the server version. There is quite a lot of things you will find here. And if you want Fluent Editor for free, you can download it, and you can use it for free if it's for academic use. If not, you can contact us. Okay, so I think that I will stop here, and if anyone has any questions, I can answer them about our reasoning, Fluent Editor, or whatever. So let me see here. So the question about so the question about REEF, yes, REEF is I think that so the question is if OWL-RL and REEF are related. So I think somehow they are, but I think that to my understanding, REEF is another format for writing rules, and while OWL-RL is using OWL to describe to describe knowledge that can be processed by a reasoning a rule engine. So this is the main difference, let's say, between these two, but probably, well, I don't know, they are compatible, so probably you can express, you can reason things in REEF from things that are in RL, but I'm not 100% sure about this. So if the tools support other languages, if by language you mean like English or other languages, right now we have implemented the controlled natural language in English, in Polish, and we have a first version of German, and but in general, as this is an interface with which you interface yourself with the ontology, then you can change the language quite easily. And for example, one of the things we are currently working on is, for example, using labels to show the name of the things instead of using a hard name, let's say. Oh yes, so there is a question about yes. So yes, there is another in this tool part you will find another part, other things that extend. So what we are trying to do is use as much as possible the semantic technology to and help people to use semantic technology. So another thing that maybe you are interested in is that we have an R plugin that is working on R, and it's making somehow some kind of bridge between R and semantic technologies. And using this R plugin, you can actually use semantic technologies standards. So, for example, you can use the reasoner, materialized graph, SPARQL queries, or things like this. You can use it inside R. And also we have many tools that uses SPARQL and Excel together. So you can, for example, download SPARQL query from Excel or things like this. Okay, let me see if there are any other questions. Okay, so the question if I was speaking about semantic web or Fluent Editor. So I was speaking about semantic web because semantic web is the base of everything that we do, and I think that what I wanted to give you today is an introduction of what the semantic web is and how to actually modify and create knowledge using all kind of semantic web technology. So this is why I'm showing you Fluent Editor, because I think it's a tool that is actually putting together all of this in one place. So it's useful in this way. Then it's mostly for people that are working as engineers for modeling the knowledge. And then we also have other technologies that are more for user friendly, so for user interface that are using the server part. I want to stress this, that Fluent Editor is fully compatible with standards, so you can export, import everything that you wrote or you have written in startup format, so AL or RDF, and so it's not something like that is something like that is that you need to use Fluent Editor. If you start to use it, you need to use it all the time, but you can go in and go out from Fluent Editor. And this is why also we have added the export and import from Protégé, because there is a fully interoperability. So if you want to use Protégé from Fluent Editor or back, then it's there's no problem. Okay. So I think that that's enough. If you don't have, yes, I don't see any new questions. So for today is enough. If you are interested in these kind of things, you can understand. You can see the other webinar that we made a bit more advanced about reasoning and very complex problem that you can have while reasoning. You can find this in our YouTube page, and in there you will see we will speak about some things. So we have spoken about things that are are logical for a reasoner, but are not very intuitive for they are not very intuitive for human beings. And so, if you are interested, please take a look. And probably we will have another webinar about the Ontology, the server part that we are developing to show you even more how to use semantic technologies to build applications. And so if you want to contact us or everything, you can just write on our site. And if you have any ideas, we are always open to new ideas, and also we are working a lot with universities to develop new features and to help them go on with research. So if you are interested, just let us know. Yes, I forgot. Everything that I have said today was recorded, and you will have the full recording in. We will put this in YouTube, and also the slide we will put them somewhere. So thank you very much, and hope you liked, and see you soon.